All right, everyone, let's get started. So today we are going to be discussing the attention mechanism, and specifically the self-attention mechanism, which is one of the building blocks for transformers, which is what we're going to talk about tomorrow, since we have Wednesday and Thursday class this week. So we're going to get started with just a brief refresher on the recurrent neural network that we discussed at the end of last class. And then we will move forward with describing why attention was created, what it does, and finally how we can implement it efficiently within the context of self-attention. So let's start by first doing an overview of the recurrent neural network. All right, so if you remember, let's say we still have our default example prefix of students opened there. And now for each of these tokens, we have an associated word embedding. Call it C1, C2, C3, same as before. And now in the recurrent neural network, remember our goal is we have a global hidden state, and we are making updates to that state left to right every time we observe a new word, right? So we start with this hidden state. Actually, let me move this. What just happened? Sorry. Okay, there. So we start with this hidden state H0, which at this point we have seen no words of the sentence, so this memory vector, this hidden state, has no idea what the sentence or the prefix even contains. Now we're going to create a new hidden state, H sub 1. And now remember our RNN update equation, right? Hn equals f of w h, h n minus 1, sorry, this is an h, plus w e c n. So this transition here, we're using the parameter matrix WH, and then over here we're using the weight parameter W sub E, which is corresponding to these word embeddings, right? So we are basically taking two matrix vector products, adding them together, applying a nonlinearity, and that's how we get our hidden state H sub 1. Similarly, we get hidden state H sub 2, and here finally we have H sub 3. Let me just get some more space here. All right. So now, given that we have this network, our goal is, of course, to predict the next word at time step 3, right? So given students open there, I want to predict the word books. So this goes into the softmax layer. And at the end, my goal is to predict books. And I do this using, then another matrix vector product with my W sub O matrix, right? And then I get a distribution over the vocabulary. I compute the cross entropy loss. And then when I'm doing gradient descent, which is the other thing we talked about in the last class, I'm going to compute the loss at this time step here, and then it gets back propagated through this entire series of computations that we've conducted up till this point to get to the softmax layer at this time step. So this refers to the gradient flow. And remember, in back propagation, we are computing the gradients closest to the output layer first, and then caching some of those partial derivatives and reusing them to compute the derivatives of parameters later down in the network. So one thing you might notice if we look at this diagram is that we actually have repeated usages of the same weight matrices, WH and WE, right? So how does the gradient computation work? Actually, and we're not going to cover this algorithm in detail, but you can derive it yourself. RNN gradients is computed through an algorithm called backpropagation through time, which basically means you, as usual, work your way from the end of the network to the beginning, but you accumulate the gradients for these two parameters, W sub E and WH, which are used multiple times in the computation. So you can kind of view this recurrent neural network as an unrolled feed-forward network and compute the gradient accordingly. And you can see that you derive this algorithm backprop through time. But we're not going to discuss that at any more length. You don't have to know about it or anything else in the class. Okay, so at this point, this should all be pretty clear. Any questions about recurrent neural networks and how their operations work? Let me check on YouTube. Okay, seems fine. All right, so let's continue with the next thing that I want to discuss, which is how do we practically train these kinds of models? I've described right now a single prefix, students open there, and I compute the loss on the very last time step and then backprop into the parameters to make the model predict books better. However, let's say the correct sequence in my training data was students opened their books and then went to sleep or something like that. So it would be terribly inefficient if at every single time step in this network, in order to predict the next word, I would have to recompute all of these hidden states and gradients and basically treat every single prefix as a separate example in the network. There's no reason for that, right? So what we end up doing in practice, let me just erase some of these arrows here, or maybe better yet, I will just use a different color. Sorry, it's going to get a little messy here. So what we do in practice is at every single time step, we are going to just apply a softmax layer on top of that hidden state in order to predict the next word, which we can do because at time step 1, I have no knowledge of what happens at time step 2. And at time step 2, I have no knowledge of the word that occurs at time step 3, right? So basically, I can put a softmax layer here. And the goal will be to predict opened. And I can put one here also. And here I'm going to predict there. And now you can see that at 3 time steps, I have 3 different predictions. And so when I compute the gradient, now it gets even messier, right? Because now I have a loss computed at each time step, not just the final time step. And so now this is going to flow backward into the network. This error signal is going to flow backward into the network. And you can imagine, like, from the very simple scalar example of gradient computation that we looked at in the last class, something like this gets way trickier to keep track of all of the different derivatives and things that we need to sum together in order to finally do the gradient update. Do you have a question? Why are we doing what? So the reason is for efficiency, right? If I have a sequence, students opened their books and went to sleep, each prefix of that sequence, like students opened their books, blah, 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 each of those gives me a potential training example for my language model, right? But I don't just want to treat all of them independently and re-encode the same thing every time, right? So this is a way where I can pass in a single long input sequence and have a next word prediction happen at every single time step. So I don't duplicate any computations across the sequence. Is that clear? Okay, but then we also have to talk about what happens when we have multiple losses being computed at each time step. So remember before, we looked at the loss as the negative log probability of opened given the prefix, right? Students. Oh, sorry, not opened, books. Given students opened there, right? And last class we talked about how this is just the cross entropy loss with regard to a one-hot training distribution where 100% of the probability in the training distribution is put on books because that's what occurs in the training data. But now we actually have 3 different loss functions, one at each point in the sequence, right? So actually, this is the loss at time step 3. At time step 2, we have this loss of opened, oh, sorry, keep saying opened, there, given students opened. And then at the first time step, we have this loss of opened given students. Right, so I actually have 3 loss functions here, and I can even have a loss at the first time step on probability of predicting students given the start of sequence token. But for now, let's just say I have these 3 different loss functions, and I've computed all of them through one pass through this sequence, right? So, of course, I would like a way to have a single loss over this whole sequence. That would be good for keeping track roughly of how good my model is doing at predicting the next word across this sequence or more broadly across a batch. And so what we do in practice is we will compute the combined loss as just the average of these token level next word predictions. So this is the average negative log likelihood of the ground truth next word over all tokens in the batch. And so what is a batch when we're talking about language models? It's not just a single sequence. It's actually multiple sequences. Each of these sequences is considered one training example. So let's just have an example of a batch here. I might have my first example, students opened their books. I don't know. People walked their dog. I don't know. The classroom fell silent. So maybe I have like many different sequences. All of these are packed together within a single batch. At every single token in the batch, I compute a separate loss of the next word probability, and then I average all token level losses together to form my loss of that batch. That's the final loss that I will be backpropping through my network to minimize. Does that make sense? Yes?
Why are we giving same weight to every loss?
Why are we giving the same weight to every loss? That's a good question. So if we wanted to give different weights to different tokens, we would need to know how to do that, right? So maybe intuitively some tokens are more important than other tokens. There are many ways to reweight the loss to try and focus on more important or difficult predictions than others, but in language modeling, it turns out that none of those methods actually is necessary at scale. So if you get 1 trillion tokens, you will have enough examples of difficult tokens as well as easy ones to predict. And so I think broadly it's just not clear how you would want to apply such a weighting. Other questions? Let me check on YouTube. No one on YouTube. Great. All right. So now let's talk about some of the issues of recurrent neural networks. So there's 2 main issues that that we have with RNNs, and the first one is this concept of a bottleneck. So this means that for any given prefix, the entire prefix needs to be represented by the last hidden state of the RNN. So if we see up here, so we're predicting, let's say at time step 3, we're trying to predict the word books, right? What are we feeding into our softmax layer? It is just h sub 3, this hidden state, right? So this single vector is responsible for encoding every bit of important knowledge about this prefix. There's just one vector responsible for doing this. And there's a famous quote by Ray Mooney in 2014. He's a professor of NLP in University of Texas, Austin. He said, "You can't represent the meaning of a sentence in expletive vector." And so this is basically the intuition behind the bottleneck in an RNN, right? Imagine if our prefix was an entire book length, and we have just a single vector at the end that we're passing into our softmax and forcing it to predict the next word. You can see why this might not be optimal. Like, the model has to be very, very good in order to distill all the important elements of that context into a single vector in order to predict the next word. And so this is one of the 2 issues that we will try and correct with the transformer architecture. The other one is that RNNs are not parallelizable across time steps. So lack of parallelism across time steps. So this means that I can only compute h sub n after computing h n minus 1, right? So the operations necessarily have to happen sequentially, which means that it's going to be very hard for me to scale this to longer sequences and bigger and deeper models. So ideally, at least during training time, it would be great if I had a way that I could compute all of the time steps at all positions at once without requiring this dependency on the previous hidden state. Okay, does that, both of those make sense? Yes.
Sequences may not have the fixed length.
Right.
So some may be long, some may be short. So the L4, L5, they have more nulls or padding.
Sure. So like here, right, these are all, so the question was, these sequences might all have different lengths and be in the same batch. So are you asking what we do?
Right, so open bias, say, I think more towards shorter sequences.
Oh, I see. Yeah, so I guess the average length in your data set will certainly bias when the model decides to put high probability on the end of sequence token. So if you imagine my entire data set consists of only sequences up to 5 words long, then if at test time I start generating and I generate like 5 words, the model might put 100% probability on the next, the end of sequence token because it's never seen anything longer before, right? So yeah, that could happen, but in practice, the sequences that people are training on are quite long and diverse, you know, with a model like ChatGPT. So we don't really see these artifacts, but so it depends on your training data quite a bit. Other questions? All right. So these two issues have motivated researchers in 2017 to create the transformer. And even before that, in about 2014, when this quote was originally said, people in the community decided to tackle this bottleneck problem. And how can we get around the bottleneck problem in recurrent models? They developed the concept of attention, which is going to be our focus of this class, and also we're going to expand on it and make it more complex in the next class. All right. So just some history first. It was developed initially for RNNs and for the task of machine translation. And you can see the papers that are linked for the readings. This paper was by Badenau and Cho. Oops. And then later, Vaswani et al. In 2017 dropped the recurrent aspect and created a fully attention-based architecture, and this is known as the transformer. Okay, so the transformer actually addresses both of the issues that we just discussed. The bottleneck is addressed through attention. The lack of parallelism is addressed through the self-attention mechanism that was popularized in the transformer. So this was also introduced by, introduced for machine translation initially. Obviously now it's used more generally for language modeling and any sort of text processing task. It was introduced by Google. And now some people at Google are kind of sad that they just put out this paper instead of like keeping it private and making their own giant language model. And instead, OpenAI took this and scaled it up and made ChatGPT, and now we are where we are today. And a key property is the hidden state at each time step is independent of the hidden states at all other time steps. And so we actually have the ability to parallelize this architecture. Okay, so that was a bit of history. Let's talk about how this actually works. So if we get back to our original architecture here, let me just show it up here. So what we want to do is get rid of these dependencies here And we also want the ability for this previous hidden state here to be a direct function of the word embeddings of everything that it's seen so far, and independent of the previous hidden state, so all the vectors at this top layer. So that's what we're aiming to achieve with attention. Let me just undo these so this figure is mildly readable. All right. So I'm going to start. If you look at the videos for prior semesters, I describe how attention is implemented within recurrent neural networks, but I'm going to skip that this year because I do want to get to the transformer as fast as possible. If you are interested in the original formulation of attention, you can watch the previous lecture videos. But for now, I'm going to focus immediately on the most relevant form of attention, which is self-attention. So we're going to start with our same prefix, students opened there. But we're going to follow a very different process for obtaining the hidden states that we pass through the softmax layer. So the very first thing we're going to do is create 3 projections of each of these word embeddings, C1, C2, and C3. So if you remember before, in the recurrent neural network, I immediately projected this word embedding into the hidden space using the W sub E weight matrix. Here, I'm going to do something different. So let's just look at C sub 1. I'm going to create 3 different projections. So this is Q1. This is what we call the query vector. This is K1, the key vector, and V1, the value vector. So let's just take a look at how we compute these vectors before we talk about why they're called what they are and what their role is in this process. So Q refers to the query vector, and we compute the query vector here as Q1 equals F of W sub Q C1. So again, simple linear layer. There's a weight matrix W sub Q that's associated with this query projection. We also have keys. So here K sub 1 equals F of WK C1. So it takes the same word embedding as input, but applies a different projection matrix to get the resulting vector. And finally, we have the value, which is, I'm sure you can all predict, W sub V C1. So I can compute all of these using 3 different linear layers to get these 3 projections. And now I'm going to do that for every single position in this sequence. So let me just copy this so I don't have to. Okay, so here I have, oops, all right, whatever, let's relabel these, Q2, K2, V2, and Q3, K3, and V3. So just like we computed Q1, Q2 equals F of W sub Q, C2. So note that we are using the same query matrix W sub Q at every single time step. And this is true for all of these keys, values, and subsequent time steps. So we have just 3 weight matrices, W sub Q, W sub K, and W sub V. These accomplish this projection step. All right. So now remember that our high-level goal of any language model is to get some hidden state that represents the meaning of the prefix, and then we are going to put that into the softmax layer. So we already said that recurrent neural networks have this bottleneck in that they force the network itself to decide at every step, like how much of this memory should I remove and how much of the new word should I add to update this vector. And this process is very complicated, so it can cause a bottleneck effect. How do we get around this with this, these weird projection vectors that we have? So let's provide some intuition first. Let me just remove these. So these two projections, the query and key, are used to compute attention scores. So intuitively, an attention score tells you how important is this word to predicting the next word at the end of this prefix. So some words like the, right, are probably not very informative when it comes to predicting the next word, whereas in this particular prefix, I really would like to know that students is part of the prefix, right, because that gives a lot of constraints on what could be opened. And so similarly, if you consider a much longer context, some of the words in that context are going to be a lot more helpful to you than others. And this is the point of the attention mechanism, is to allow the model to decide which words are most important and then put more information from those positions into the hidden state than otherwise. So then what are these value vectors used for? Well, that's a terrible bracket. These are actually going to be what goes into the hidden state when we compute it. So query and key are used only for computing these importance scores. The value is the thing that we are going to use to actually update our hidden state. So it's used to encode information used to compute hidden state. So this probably won't make any sense right now, but when we look through a step of the operation of this mechanism, it will make more sense. So let's get started with that. And we're going to start here with time step 3. Before I do, let me just check on YouTube to see if there's any. Okay, there's 2 questions. Why do we directly use the hidden layer directly as a next word probability distribution and not use a weight matrix to convert from the hidden state space to the next word probability distribution? Not really sure what the question is asking. We don't directly use the hidden layer as a next word probability distribution because that doesn't make sense, right? The probability distribution should be over the space of the vocabulary, which is why we use this weight matrix via our softmax layer. So I think you're referring to the softmax layer. Sentence embedding does a similarity thing by representing sentences in a vector. We won't get any problem there. That's a good question. So, many of you might have used models that compute sentence embeddings before, which is given a sentence, you get a vector as output, and you can use this vector for whatever you want, like clustering or classification or things like that. Does this have the same issue? Yes, it does. I mean, granted, sentences are pretty small, and even Ray Mooney, if you talk to him today, will say, well, maybe he was wrong about sentences, but right in general about you can't just fit the meaning of an arbitrary text into a single vector. I mean, we will see in the future if he's proven wrong, but currently there are limitations, right? If I have a 100,000 word long text and I compute a vector of this text, I can't expect that it will have all the knowledge of the narrative and the important events and topics that are present in that document encoded into this single vector, right? We don't have a powerful enough model at this point. So all of these methods, embedding-based methods, have limitations. given we have to calculate the attention scores of each word with the rest of the contents, don't you think that does not make a lot of sense and computationally very expensive? Let's get to the computations, and then you'll see why it makes a lot of sense and is actually cheaper than the RNN at training time. So I'm going to get back here. Did you have a question? Yeah, so the question is, in the query key and value projections, this F, this is a nonlinearity? Yes, this is always going to be a nonlinearity. In this case, it's the rectified linear unit or some variant of that. All right, so let's look at the third time step here. I hope I don't need more space, but we'll see. Computation of hidden state at time step 3. So here we have the input students open there. We want to get a vector, pass it to a softmax layer, and have it predict books, right? This is our same example from before. So what we're going to do is take the query vector Q3, and we are going to compute 3 different dot products. We are going to compute the dot product between Q3 and K3, between Q3 and K2, and Q3 and K1. So specifically, our attention scores is going to be a vector of 3 numbers. So we're going to have Q3.K1, Q3.K2, and Q3.K3. So I get these dot products, right? And if you remember when I talked about the softmax function, I said you're going to see this function over and over again in this class, and we see it right here. So the point of an attention-based model is that we are going to normalize all these dot products such that this vector becomes a probability. So we're going to take the softmax of this vector, and now you can start to interpret this result as intuitively probability distribution, where more of the probability mass is going to be distributed over tokens that are more important for the prediction of the next word. Does that make sense? So what I might get as a result of doing this process is Q3K1, Q3K2, Q3K3, a distribution where, let's say, 30% of the probability is here, 50% here, and 20% here, which means that if you were to interpret it just looking at the distributions, the model thinks that the word opened is more important, or at least looking at the representation of this word is more important than looking at the current word embedding there. Obviously, this is just made up, and in practice, its distribution could be very different. I will also add a note that you can't directly interpret these attention scores in the way that I just did. You don't know if just because the model assigned 50% to this token, that it actually thinks that token is most important. That's because these deep transformer models have a lot of layers, and they get composed in these nonlinear functions. So just because the model assigned 50% probability to some hidden state at layer 17, that hidden state itself is a function of all of the words in the original text. So you can't really decide, what does it mean that it put this attention here. You can't kind of decipher what that means in practice, but we can use it as an intuition to explain what the attention mechanism is doing. And it does make sense in this one layer setting where there's no intermediate layers to make the process more convoluted. All right, so we have these attention scores. Oh yeah, do you have a question? Yeah, we'll get to how you make this deeper after we go through the computations at a single layer. But yeah, in general, we'll see how it works. Okay, so I have this distribution, but this still does not give me what I want, which is some vector that I can feed into the softmax layer and get a prediction of the next word. So this is where these value vectors come in. Remember, I haven't used them so far. So what I'm going to do is essentially use these weights here, the 0.3, 0.5, and 0.2, to compute a weighted average of all of the value vectors in this sequence. And that's going to form my hidden state for the softmax layer. So specifically, h sub 3 equals 0.3 times v1. That's the value vector at time step 1. The 0.3 comes from the attention score that was computed by the query and key dot product, plus 0.5 times v2 plus 0.2 times v3. So essentially, I'm taking a weighted average of these purple value vectors where the weights are determined by the query and key vectors, as I just described. So now this h sub 3 here gets passed to the softmax layer, and we predict books. So this is just a one-layer self-attention network. But you can see that the computation of h sub 3 has no dependence at all on h sub 2, right? There's no mention of h sub 2 anywhere. In fact, I can compute h sub 3, h sub 2, h sub 1 all independently of each other, which we will see later contributes to making this model very efficient at training time. All right, so any questions about these kinds of computations? Yes?
What we do the parallelization if we are predicting one word at a time? Since we have to first predict
Yeah.
one word to get to.
That's a good question. So the question is, let's say we're generating a piece of text. How are we going to parallelize across different time steps when we haven't even generated word 4 yet in order to generate word 5? That's, so basically, this parallelization can only happen at training time, not at test time. So at training time, I already know the full sequences, right? I know word 4 and word 5 and word 6. Some human wrote them for me, right? So I don't need to generate from the model in order to get those words. At test time, I do have to proceed one word at a time, just like in a recurrent neural network. So that's a good point. Maybe I'll write it down up here, just so everyone is clear. Attention, self-attention is parallel at training time, sequential at test time. Because it doesn't matter if we don't have a dependence on h sub 2, we still need to find the word that comes at position 2 in order to predict h sub 3. All right. So one little wrinkle here, yes, go ahead.
One thing that I fail to understand with very key and value are the weights that we're using, the Q1, the projections that we're using. They're just arbitrary parameters that are decided while training, right? And the query key and value, these words we're using to intuitively assign some function. Am I right?
Yes, so WQ, WK, WV are all learned parameters of the network. So they start out randomly initialized, and then through the gradient descent process, they are updated in order to, the goal is to just make better predictions of the next word, right? Yeah, yes. Why do we need both query and key? So let's say I just had query vectors and I had no key vectors, and I'm computing these dot products with each other, right? Intuitively, let's imagine I'm computing, say, the normalized dot product, like a cosine similarity, right? So then Q3, I have to compute the dot product of Q3 with itself, right? Which will give it an unfair advantage compared to any other vector, right? Because these two vectors are identical. So essentially, it's a way to allow the model to give a low dot product to the current position of the sequence if it needs to put that probability mass elsewhere. That's one reason. Another reason could be that we benefit from adding more parameters to the model. So here we have a W sub K matrix, which is another thing that gets to be learned and can help us stack more parameters into the model. But yeah, there have been some ablations of these without key vectors, without value vectors, right? Why do I need a value vector? I could just use the same query vector to compute the dot product and do the hidden state weighted average. But it turns out that having these 3 different projections is better. So that's why people are still using it. Yes?
Just going in the opposite direction, why not have one more vector?
Yeah, you could have one more vector. I think at that point, people probably have observed a marginal benefit to adding more parameters within a single layer, as opposed to just stacking more layers that look like this. There's also historical reasons, like this architecture has been shown to work well, and it's shown to be scalable. So, there's a lot of potential improvements or changes you could make to this architecture, but in order to validate them, you have to train at some enormous scale to see if it is competitive, right? So, this architecture is baked into PyTorch as a primitive. You can just add a transformer layer and it does this for you. So I think there's a lot of legacy code, and also that's kind of keeping people within this framework. All right, so I wanted to talk about one other thing that's very important in this architecture compared to the recurrent neural network, which is this idea of the position of a word in the sequence, right? So in a recurrent neural network, since it operated at left to right, it could inherently keep track of where in the sequence it is, how many words it had observed before. It's certainly capable of learning all of these things and encoding some notion of where in the sequence am I right now and how many words have I seen before. But if you look at this computation here, no part of this has anything to do with the order of these words, right? I'm taking these dot products independently of the other words, and if C1, C2, C3 were in a completely different order, this hidden state would be the same, right? Which is obviously undesirable. So in practice, let me just get some more space here. So in practice, what I do is, let me choose a new color. We add what is called a position embedding to each of these initial word embeddings, C1, C2, and C3. So this is a bit of a hack, right? Because our model currently does not take into account position. The way we do it is we add a separate embedding that has some notion of position, like the embedding P sub 1. These are called position embeddings. P sub 1 is fixed for the first position. So given a completely different sequence, I would add the same P sub 1 to the first position of that sequence. Given the second position, I will always add P sub 2. This is exactly the same vector. And the position embedding could be learned, it could be fixed. We will actually have an entire lecture on position embeddings because, believe it or not, they are very important in modern NLP, especially when scaling to very long sequences. So imagine that these are learned embeddings. The position embeddings are parameters of the model just like the word embeddings. That means, just like with any language model, I'll have to define the maximum length of sequences that my model can process. So let's say that's 100 words. My model can only process 100-word long sequences due to memory limitations or whatever hardware constraints we have. So that means I have 100 unique position embeddings in my model, right? That also means that at test time, if I wanted to generate a text that's longer than 100 words, my model will have no idea what to do, because once I get to 100 words, I run out of position embeddings and it has no idea what to do about the 101st word. It doesn't have a parameter there. So that might motivate us to choose a different way to represent our position embeddings, such that the position embedding is maybe not learned, but rather some sort of deterministic function where the model can kind of learn to interpolate between positions that it's seen during training and use that to estimate position embeddings that it can still leverage at test time for longer sequences. So there's a lot of interesting work being done on position embeddings that are allowing these models to scale to much longer sequences at test time, but that's for later. So just keep that in your head. There is some sort of position embedding that tells the model roughly this position is different than this one, and this is being added to the model at the very first layer of the network. So the input to the network is just the word embedding plus the position embedding. Yeah, this is an element-wise addition. You could try something else, multiplication, whatever, but yeah, the
essentially we still learning just the iterator, which is the or will we be learning two separate vectors and BI separately and C separately?
So again, like position embeddings can be learned, but they also can be set to like hard-coded functions. But yeah, if we're learning them, then we learn P1, P2, P3, as well as C1, C2, C3. Because like imagine students can occur at the first position or the second position or the 50th position, right? So we don't want to learn an embedding for students at the 50th position, right? We want to learn an embedding for students that regardless of what position, we can just add a position embedding to it and the model will know how to treat it. All right, so that was the detour about position embeddings. Now let's get back to our favorite prefix, students open there. Note that we have only done the computations at the third time step of this network, right? So let's go ahead and do this for the second time step. I'm just going to copy all of this again. Okay. Put it down here. Okay, so computations at second time step. All right, so here, oops, okay. Maybe fix that. So here, I'm at this position and I want to predict the word there, right? So to do that, I take my query vector and Q2, I compute the dot product with K2 and the dot product with K1. Now, why don't I compute the dot product with K3 here? Like, what would that mean? Exactly. So I know that the word embedding of time step 3 is associated with the word there, right? Which is the word that I want to predict at this time step. So if I look at the word embedding for there, which note that Q3, K3, and V3 are all functions of the word embedding for there, note that V3, if it ever comes into my hidden state, it is just basically cheating, right? It tells me that the next word is there. If the model put 100% probability on the third time step here, it wouldn't need to learn anything about language, right? It would just need to learn that, you know, the word embedding associated with the next time step is the one I want to predict. And we have a completely useless language model that gets 100%, you know, perplexity of 1, right? But we can't use it for anything. So we don't want to do this, and instead we will only compute these two dot products here. So what does this look like? Well, our attention is now softmax of this vector, q2.k1 and q2.k2. And our distribution looks like q2k1, q2k2. Let's just write out q2k3. So we might have some probability on this one, some other probability on this one, and this has to be 0, right? No q2k3 because of cheating. So however we implement our language model, it cannot allow for any non-zero probability to be put on time steps ahead of the one that we're currently predicting for. Right, so here h2 equals 0.3 times v1 plus 0.7 times v2. We feed it into our softmax and predict there. And you can imagine doing the same thing for the first time step, except now 100% of the probability goes on Q1, K1, and 0 everywhere else, right? So the model only has one time step that it can focus on. Does that make sense? Okay, so let's just write this out more explicitly. No dependencies between, wow, that was so bad, between H1, H2, H3. So that means we can parallelize, which we will see shortly. Parallelize. And also we are reducing the bottleneck effect by having this weighted average. Now, the final hidden state no longer has to carry all of the information that's needed for predicting the next word, because we have this attention mechanism that can kind of provide shortcuts to other value vectors that might be potentially very far back in the sequence, right? But if the model judges those to be important by computing this dot product, it can increase the effect that far away vectors have in the current hidden state. This, theoretically, an RNN could do things like this, but it's very hard to train them in a way that they are able to take advantage of time steps that are very far in the future. In the past. All right, let's see if there's any questions. Why do we need to learn positional embeddings? They should reflect the position of the word, right? That's a good question. I mean, how they should reflect the position of the word, but also be useful to the model, right? And since the model is rapidly changing, it's being updated through gradient descent, whatever position embeddings you hard code might not necessarily be the easiest form for the model to understand. But yeah, you don't need to learn them. I won't go into any more detail here, but we will have a separate lecture on position embeddings where we'll learn more about that. All right. So now let's take a look at basically the reason why people like transformers during training, which is the parallelization that we can do. So maybe I'll start a new page. How to parallelize. And when I discuss parallelization here, I mean, how can we essentially vectorize this computation to compute multiple time steps, compute the hidden state at multiple time steps in as few operations as possible. So we want to just pack the matrix vector products and limit how many of them we do. We can take advantage of GPUs by doing fewer but bigger computations, right? Because a GPU will inherently parallelize, like giant matrix products for us. So let's take a look first at the attention vectors that we want to compute. And I will just call this A1, A2, and A3. A1 is the attention distribution at position 1 of the sequence. So the dot product we want to compute here is Q1, K1. For A2, we have Q1, K1, Q2, K2. Oh, sorry. Q2, K1. Q2, K1, Q2, K2. And then for A3, we have Q3, K1, Q3, K2, Q3, K3. And remember, we are not including these other dot products in the first or second time step due to the cheating effect. All right, and now let's draw out our query and key vectors here. So I have Q1, Q2, Q3, and I also have K1, K2, and K3. And so I'm looking for a computation that will allow me to obtain all of these dot products that I need for A1, A2, and A3 in as few computations as possible. And so if you look at this, you can start to see an easy way to do this. Let's consider we put all of these query vectors into a matrix row-wise. So the first row is Q1, the second row is Q2, the third row is Q3. And let's put all my key vectors into a column matrix here where the columns represent the keys. So now, if I do this matrix product here, what do I get? I actually get a bunch of, I get the dot product between all of the queries and all of the keys as the result, right? So my resulting vector here, sorry, I should have made this look better, but I will get at the end a 3 by 3 matrix, right? Where the queries are over here, the keys are over here, and each element of this matrix is one of the dot products of the query and the corresponding key vector, right? So I don't need to compute all of these time steps independently of each other if I can just compute all of the query and key vectors for all time steps, put them into 2 matrices, and then take this matrix product, right, which gives us these dot products that I need for all of the time steps attention distributions. So now if you look at this, for time step 1, what am I interested in? I have, basically I want this one, right? For time step 2, I want these 2, and for time step 3, I want these 3. These elements of the matrix here are associated with future tokens, and I don't want any part of those in my final computations, right? These cells have info about the future. So we need to exclude these or mask them, which is the terminology that we use. So let's see how we can actually implement this mask. And the way we can do that is through when we apply the softmax function. So remember, we want to take the softmax of A1, A2, A3. Those form our final attention distributions. So how can we exclude these red cells when we're computing the softmax? Our computation is going to look like this. So we have this matrix here, the 3 by 3 matrix that contains all of these dot products. And what we're going to do is first multiply this matrix element-wise with what we call a mask matrix. So a mask matrix is going to be 1 at all the positions we want to keep, which are these purple positions over here. And it's going to be set to negative infinity for all of the other positions. So why do we set it to negative infinity? If you remember in the softmax function, we are exponentiating each element of this matrix, right? So if we set some element to negative infinity, when we exponentiate it, it will go to 0, right? And that's what we want. So this is called our mask matrix. And so now, just in a single computation, single matrix product, we have all of our attention distributions, right? So this is really great. But the other thing we need to do is get the weighted average of the value vectors, right? And we can do that similarly with another matrix product. So let's call this our attention scores. And let's say I now have this softmaxed attention score matrix. Now I can just multiply this matrix with our value vectors, where I also just arrange them into a matrix. And the result gives me my hidden states nicely arranged as rows of the resulting matrix. So to get from the query and key representations to the hidden states, I essentially need to do 2 matrix products. One between the queries and the keys, and another with the resulting normalized attention matrix with the value vectors. So if you didn't follow this, you can go back and try it out for yourself and make sure the math works out. But here, essentially, we computed the hidden states with just a couple of matrix products for the entire sequence. Yes? Are there any limitations with regarding like the size of the? Does it get worse after a certain point? Yeah, so like I guess you're referring to the dimensionality of the query key and value vectors, which these are hyperparameters of the model, right? So the designers of the system will choose these based on how much memory they have in their GPUs, how many layers they want their model to have. So if they have a lot of layers, then maybe they don't have space to have very large dimensionality for these vectors. And as we'll see next class, there's also an added complexity where we might want what's called a multiple head attention, where instead of just having one query and one key per time step, we have many different queries and keys for a single time step, which adds to the complexity, but also has intuitively some benefits where different heads can focus on different parts of, or different aspects of the text that might be interesting. So maybe one head can focus on syntactic properties of the prefix, others can focus on semantic properties. That's just an intuition. But yeah, it's all just a hyperparameter loosely bounded by the desired number of layers, which is another hyperparameter, and everything finally is bounded by how much total compute you have. Other questions? How is backpropagation done here? Yeah, so here you can see we have these matrix products, so the gradient will obviously flow. So this H1, H2, H3 all gets fed to the softmax layer, and then we compute our loss, right? So then we backprop through the softmax layer, through this hidden state matrix, through the value vectors, through the query, the key vectors, and all the way back down to the word embeddings and optionally the position embeddings. So obviously that's very high level description. If you actually write out the derivatives, it can be very hairy. You have multiple softmax functions, and you also might have multiple layers and other things going on in the network, as we'll see tomorrow. So we won't explicitly write out the gradient computation for this network, but you should be able to derive it if you really wanted to by looking at the equations governing the model. Oh, is there any difference in the algorithm that's used? No, it's all just the chain rule and caching, the normal backprop algorithm. Other questions? All right, let me check on YouTube. Why do we have to normalize Q? What is this reaction thing? All right, Q times K matrix before doing a cross product with V. So we are viewing the query and key product as the attention as a distribution, probability distribution over time steps in the prefix. And so that's why we do this normalization. Otherwise, you might have potentially unbounded dot products that could affect the training, could worsen training, and also potentially not give the model as good of an idea of the importance of any single position. All right, so next time we will talk about the transformer, which is essentially taking this self-attention mechanism and scaling it to different layers, adding more bells and whistles. So I'll see you tomorrow.